All right, this is our second installment of our summer assignment video, and we are now on page 8, which is the top of page 8 of our packet. And we're going to talk about how to display our two categorical variables in our favorite type of graph, which is my favorite type, which is the segmented bar graph. So first of all, you could do a side-by-side bar graph if you have two variables where, remember, the bars don't touch on a bar graph, and you would put the two variables on the x-axis. So if you look down below here, I'm gonna star it. This is a side-by-side bar graph. So you see you have yes and no for were they a member of the environmental club on the x-axis, and then you have the breakdown of within those groups, the percent breakdown of never, rent, and own. So that's one way to do it, and then you can compare the bars of never to each other, and then etc. The red ones, rent, and own. I'm not really that much of a fan of that one as much I am of this one on the right. That is called your segmented bar graph. So it's cool because you have two bars. The bars go up to, they both go up to percent of 100%. And then basically we find the percent breakdown of the variable of snowmobile use within the yeses and within the nos. And we create segments within each, accumulating up to 100%. And the reason why this is nice, this is most on the AP, by the way, over the other type, is you can directly compare across the segments and make a comparison about the proportion or percent, in this case, of snowmobile use. So for example, if you look in the green segment, you see green is own, and you could see there's a greater percent of people who own snowmobiles if they are not in the environmental group over those who do. And then if you look at the purple, you see the nevers, there's a greater percent of people who never used a snowmobile and those who are environmental club members over those who are not. So yes, you could go across and create three separate sentences comparing the percents of each. So very important to note when we're describing this, you want to compare percents or proportions and not counts or numbers or frequencies. So what do I mean by that? I'm going to say there's a greater percent of those who never owned a snowmobile than there were who never, sorry, let me say that again. There's a greater percent of those who never owned a snowmobile in the people who are members of the environmental club over those who were not a member of the environmental club. I'm not saying there's a greater amount of snowmobile nevers, because the problem is that the totals could be out of different totals. So we never really want to compare counts. We just want to compare percents. So the one thing you need to really know about the segmented bar graph is it shows the two variables at once. And it shows segments almost like, you know, in the earth, there's like sedimentary rocks with the different segments kind of breaking down within it. That's kind of what it shows. The bars go up to 100%. Every bar has to go up to 100%. And then it shows the breakdown of the one variable within each bar. And remember, we compare percents across. It's easy kind of to compare the percents across the way. All right. So I do believe that this is going to be on the AP, whether it be one multiple choice or one free response. They've asked you to make a segmented bar graph yourself, and they've also asked you to analyze it in the form of a multiple choice. So basically, our question is there an association or is there a relationship between the two variables? Okay, so in this case, if we look at my segmented bar graph over here, is there a relationship between being a member of the environmental club and using a snowmobile? And the answer is yes, there is a relationship. Yes, there is a relationship or is an association. Because if I know that the person was a member of the environmental club, they are more likely to not have ever used a snowmobile over those who are not a member. And if I know the person is not a member of the environmental club, they are more likely to own a snowmobile over those who are a member. So having knowledge of knowing that they were a member of the environmental club does impact the percent of snowmobile use. So there is an association between these two variables if the bars show a different percent breakdown from bar to bar. Okay, so if the segment breakdown is different from one bar to the next, then there is a relationship between the two because one thing is different than the other. However, if there is no association between the two variables, the bars will look exactly the same. And the segment breakdown, what's up with this marker? The segment breakdown will look perfectly equal across the bars. Something about that part of the TV that's not working with me. All right, so what do I mean by that? I mean if you had yes and no for environmental club across the x-axis, going up to 100%, and then you had snowmobile own the same, snowmobile rent, that doesn't look the same, but the percent breakdown the same, and snowmobile never the same. If it was exactly the same going across the bars, then that means there is no relationship between the two variables because there's no, it doesn't matter if the person is a member of the environmental club or not. The percent breakdown will be the same regardless of if they were a member or not. So you learned this kind of in the form of Algebra 2 trig when you guys were doing independence and dependence. Basically, these two variables are independent of each other if they have no relationship or association between each other, meaning that knowing that they're a member of the environmental club would not change the knowledge of them owning a snowmobile. Also, as you could see on the down below with the AP tips, it says make sure when comparing you're using relative frequencies or percents, like I said, or proportions rather than counts. That's what I said above, very important. And then don't use the word more, like more club members never use snowmobiles when you actually mean a greater percent. So again, you're comparing percents and not comparing amounts. All right, so that's that on page 8. Now we're going to go to page 9 and we're going to start to talk a little bit about quantitative variables. So this is where it's at, people. Most of the time we're living here this year in quantitative data. All right, so quantitative variable can be displayed in many different ways, in a dot plot, a stem plot, a histogram, or a bar graph. So here's the first one, the dot plot. So you've seen a dot plot if you took Algebra 2 and Trig last year, and the dot plot, basically, every dot is going to represent a person in the data set. Each dot represents an individual in the data set. And the x-axis is going to be labeled with whatever the variable is that you are measuring. Quantitative variable, by the way, because it's numeric. And basically all you do is put a dot for every person. So you draw your horizontal axis, which is your x-axis. It's a number line. And then you label it with whatever variable. So in this case, this was talking about soccer goals scored. So that's on the x-axis here. And then you scale it out. So make sure that you count by a consistent amount. So this, in this case, they were counting by ones. And basically don't skip numbers. So like in this case, we had 1, 2, 3, 4, 5, and then we had 9, 10. Don't make a number line that says 1, 2, 3, 4, 5, 9, 10. Don't skip the numbers, because then you don't get an idea of what where there's a gap in the data set. So you want to make sure you include all numbers in the number line from 1 to 10 and show that there's a gap here. This is important because when we describe our data set, we want to say there's a gap between 5 goals scored and 9 goals scored. Okay? So basically now we're going to be able to describe the data using a word, which it doesn't look like it's on this page, but we're going to describe if it's symmetric or if it's skewed. Okay? So in this case, you learned this in Algebra 2. If you took Algebra 2, when you draw a curve, kind of like a smooth curve, over the top of your data, if most of the data is on the left and then you have a few, these are called outliers on the right, the data is skewed in the direction of the outliers. So this case, this is called skewed right. And the reason why it's skewed right is because most of the data is actually on the left, and it's more typical that most people are going to be scoring between 1 and 5 goals, but there's a few rare people who are scoring 9 and 10 goals. All right, I don't know if this was about people or a team, but basically that's very rare to happen. So these outliers are pulling the mean or the average up, which means that it's skewing the data toward the right. So this is skewed right, and you can picture like a whale, and if the whale has a tail, the tail is on the right, it's skewed right. So this is like a whale or a fish with a tail, and the tail is on the right, skewed right. So wherever the tail is the direction of the skew. So this is called skewed right. Okay, so where we left off was we were describing shape on page 9. So in the middle of page 9, we're going to talk about the description of the shape for the 3 dot plots down below. So in the middle of the page, example 3, the first one, this one, you guys did this actually in Algebra 2 and Trig, is approximately symmetric and bell-shaped. I don't know if it's perfectly symmetric. Unless it's perfectly symmetric, we're going to say it's approximately symmetric. It's not perfect. All right, now this next one, you see that it's skewed. So again, wherever the tail is the direction of the skew. So here, the tail is on the right, so this is skewed right, which means most of the data is on the left, and then there's a few rare points on the right. Picture a whale or a fish with a tail, and this is the tail on the right, skewed right. The mean gets pulled to the right. And then this one on the bottom here, the tail is on the left, so this is skewed left. Again, picture a whale or a fish with a tail, and the tail is on the left, skewed left. This means actually most of the data is here on the right, and then the mean gets pulled down in the direction of the skew. So that's what it says here on the bottom of the page. It says the direction of the skewness is toward the longer tail, not the direction where most of the observations are clustered. So in the last one, most of the data was clustered on the right, but the tail was on the left, so it skewed left toward the tail. All right, now we're going to turn to page 10. On the top of page 10, I want you to describe the distribution, okay? So first thing I want you to do is I want you to write down the shape. So based on what we just talked about, I want you to write the shape over here in the box for the first bullet point. So right now, stop the video and write down the shape. So when we talk about shape, we want to talk about the fact that it's skewed or symmetric, and then we also want to talk about if there are any gaps or clusters. So first thing I'm hoping that you wrote was that it was skewed, and specifically because the tail is on the right, hopefully you said it's skewed right. So the distribution of goals scored in the 20 games of the U.S. women's soccer team is skewed right. But we also notice something interesting here. We have a gap. Specifically, there's a gap here between 5 goals scored and 9 goals scored. So we want to say that as well. Now also notice that I'm using something called context here. And the context has to do with what is this question actually about. So if you look back up at the top, the context is the number of goals scored by the women's soccer team that year. So that's why I'm throwing in the word goals scored. That's going to be the context. Now, if you look at the top of this question, the question says describe. You're going to get these questions a lot on the AP. They're usually like question number 1 on the free response of the AP. It'll say describe the distribution. And that directive, describe, is actually a loaded word because that word actually means that you don't just write the shape. You have to remember the key word socks, okay? S-O-C-S, but I'm going to put a double C here because I'm going to throw in context, okay? So don't forget your socks. So describe means use socks to describe the distribution that we see. So let's start with S. The S is shape. So the first S we did, shape, socks. Now we're going to go to O. O stands for outliers. So are there any outliers or any numbers that seem like they're separated from the rest of the data? Meaning unusual observations that are separated from the pack. So yes, it looks like there are 2 numbers on the right here, 2 dots that are potential outliers. And those are rare games for the U.S. World Soccer Team because it's not typical to be scoring 9 or 10 goals in a game. So there are 2 outlier points or 2 outlier games, and they are 9 and 10 goals scored. Notice again, I'm using context here because I'm saying goals scored, which is the context of the question. And I'm using games because the dots really represent the games of the 20 games of the soccer season. So now we're done with S, we're done with O. So now we're going to move on to C for socks. The C stands for center. So center can be measured by either the mean or the median. Okay, the mean or the median. And the mean, you guys know from the past, is the average. So if I wanted to, I could find the average of this data set by adding all the points up and dividing. And that would be my average. That seems like a lot of work, but I could do that. The other thing that I could do is find the median, and that's a little bit easier. So we're actually going to go and find the median first And the median, I'm going to talk about a little later actually in the packet. But you guys learn how to find the median back in the day. The median is the middle number, right? So remember what you would do back in the day to get the middle number? You would kind of, just to find the middle number, cross out. You would go 1, 1, 1, 1, 1, 1, 1, 1. So let's do that. I think I screwed up here already. But you guys get the idea. So let's find the middle number, okay? It's probably 2, okay? So the median's probably 2 goal score. So I'm going to write that down and I'm going to show you how to find it officially in a coming page. So I'm going to write a little squiggly equal sign for now. And I'm going to write median goal scored is 2 per game. And we could also find the mean, but we won't for the sake of time. You would add up all the numbers and divide by 20 in this case. The last letter of SOX is S, and S stands for spread. So spread, you guys also, if you're in Algebra 2 and Trig learned, has to do with how variable the data is. So is it really spread out, or is it close together? So the quickest way to do it is to find the range, and the range is maximum minus minimum. We're going to talk about other types of spread later on. For the sake of this, let's just do maximum minus minimum. So the maximum number of goals scored was 10, and the minimum number of goals scored per game was 1. So we're going to do 10 minus 1 to get the range of goals scored. So 10 minus 1 equals 9 goals scored. So the range of goals scored is 9 goals scored. A pretty wide range. And again, you want to say by the U.S. soccer team to be context in the year that we were talking about, which I think was 2016. Okay? So again, I think it's really, really important to note, if you see that verb describe, I don't want you to just think, like, write down what you think. On the AP, they have a rubric, and the rubric is actually going to ask you, did you hit S, C, and S, specifically shape, center, and spread. And if you hit all 3, you're going to get an E for essentially correct. And if you only hit 2 out of 3, you're going to get a P for partially correct. If you only hit 1 out of 3, you're going to get an I for incorrect, which is a shame because even if you write one of these things correct, they're not giving you full credit, which is crazy. So again, just a note to self, describe means SOX, and you want to hit those bullet points. If there are outliers, you want to make sure you say outliers, okay? Make sure you do it in context. Otherwise, if you just write it skewed, it's like, what's it, you know? So now I want you to look at example 5, please, which is on the bottom of the page. And I want you to do this one, except this one has a different verb. Instead of saying describe, this one says compare. So not only are we going to hit SOX, which is shape, outlier, center, spread, but we're going to use comparative language in order to do that. So this is also a typical question on the AP. It would be like question number 1. They give you 2 distributions and they would ask you to compare them. So comparative language means they're going to use keywords like there's a greater median than this. There's a less median than that. There's a wider spread or a narrower spread. One of them is more variable. One of them is less variable. They have equal medians, okay? One is more symmetric than the other. One is more skewed than the other, etc. So you have to kind of compare. A typical thing that people do is they might separately list the 2 and not draw any comparisons between the 2. And that's bad because then they're not really drawing how they're related. So example would be like saying apples are red, oranges are orange, apples are round, oranges are also round. But you have to kind of like link them together. So you have to say apples and oranges have different colors. Apples are red, but oranges are orange. Both of them have the same shape. They're both round. So that's how you kind of compare them to each other. World War II started like that, whereas World War, One started like this. They have different causes or whatever. All right. Anyway, so let's go to this. So we have South Africa, and we have the UK, and it looks like they did a census, and they chose 50 students from each country, and they did two dot plots, and they wanted to compare the distributions of household size. So the variable that we're measuring here is household size. So everything you do, you want to say household size. Household size, household size. All right. So let's start with shape. I see a clear difference between shape. So South Africa to me looks skewed to the right because the tail is on the right and there's an outlier on the right. And then UK, I'll use a different color, I'll use blue, looks skewed to the left. So that's a clear difference. Clearly, Africa, South Africa, and UK household sizes have different shapes. Distributions. South Africa is skewed right when it comes to its household size, whereas UK is slightly skewed left. It looks like South Africa is way more skewed than UK because South Africa has a much longer tail on the right, and then the UK is kind of more clustered together. And that actually is a clear difference in the spread. So if you go down to spread, which is down here, it definitely looks like South Africa has a wider range or more variation or variability than UK. UK is a lot more clustered together or more consistent than South Africa. So we want to say that with the household sizes. That's a clear difference. South Africa household sizes have much greater range of sizes or greater variability or greater spread. Those are all interchangeable words than UK sizes, household sizes. Now, I don't actually have to find the range. I'm just using comparative language. So very important that you don't actually have to say the range of UK is this, the range of South Africa is that, but instead you do just have to use comparative language like the ones that I said above or in the box here, greater than, less than, etc. So I'm using the word greater than when I say that the range of South Africa is greater than the range of UK. All right, another clear difference is that South Africa has an outlier and UK does not. South Africa household sizes has an outlier household size, has one outlier, right? Whereas UK has none. Okay, again, I'm just sprinkling the word household sizes throughout to include the context. And lastly, center. So let me ask you, what do you think is going to be the bigger center, the bigger mean, or even the bigger median? Which one do you think is going to have a greater median household size? South Africa or UK? Since these are parallel dot plots, they're on the same set of axes, it's pretty clear to see that the center of the South Africa is going to be higher than the UK. And that makes sense because maybe they're having more children in South Africa per household than they are in the UK, right? So I'm just going to say the center household size, and I don't know if it's the mean or the median, probably the median would be what we would compare, of South Africa is greater than the center size of UK. All right. So we're actually done here. Notice I didn't find the actual median. I didn't find the actual range. I'm basically just using comparative language to compare the two things in terms of their similarities and their differences. You guys have done comparisons over the course of English and social studies classes over the years, so you know what it's like to compare two things together. You can now already see, before you even move forward with my class, how much writing is involved in AP statistics. You have to be thorough but concise, which means you have to hit those bullet points that they're looking for, shape, center, spread, in context, but you can't write me a novel. You have to try to get to the point, all right? So that's that. So now I'm going to give you a little time here. Stop the video and do page 11. I want you to do this one, page 11, example 6. Go. Here is page 12. Top of page 12, stem plots. So another type of way to display quantitative data is a stem plot, also known as a stem and leaf plot back in the day. What you need to know is each data piece is represented with a stem and a leaf. And stem plots are nice because you can see every single data point, just like with a dot plot. You could see every single data point represented. So it's telling us how to make a stem plot. It's saying first thing we have to do is decide on what our stems and our leaves are and separate them into stems and leaves. Then what we do is we write a vertical line, which is a line up and down like this, vertical line. And we want to put the stems first in, sorting them from low to high, or smallest to highest. And then basically we want to put our leaves in order on the right. So basically your stems go on the left and your leaves go on the right. And then you're going to list them in order with stems from low to high in this column here. And then you're going to put your leaves in on the right. And then at the end, super important, you want to provide a key. I'm going to put a star on number 4 because the key is going to tell us how to read the stem and leaf plot. All right, so here's a set of data. And you see the set of data is 2, 4, 6, 8, 10, 12, 14, 16, 18, about 20 pieces of data, okay? And these data are going to be sorted now by lowest to highest. So you could actually sort them as you go, listing them from low to high or whatever. So you could see that the lowest number we see is 13, okay? There's actually 3 13s here. So it looks like the lowest number is 13, and the highest number is 57. So when you guys do your stem and leaf, the stem is going to be the 1 and the 5, and that's going to go on the left, 1 through 5, listed in order. And then the leaves are going to be the single digit pieces that are going to be the ones place. So the stem is going to be the tens place, and the leaf is going to be the ones place. So that's going to be your 3 for the 13 and your 7 for the 57. So as you could see here, first they put in their stems 1 through 5, and then they started putting in the leaves corresponding to all the ones. So I'm going to circle all the ones with blue. 13, 13, 13. Then we have 15. So that's going to be here, the 1, 5. And then we have 19. That's going to be the 1, 9. So notice we're not writing 1, 3, 1, 5, 1, 9. The 1 is only written once on the left of the stem, and then you just write the 3, 5, and 9, representing the 3 13s, the 15, and the 19. Now we would move on to the 2s. So the 2s are really representing the 20s. So we have 22, 23, but there's 2 23s, so they're here. 24, and two 26s. 1, 2. And then you're done with the 20s. And then you would move on to the 3s, the 4s, and the 5s. Now, if you had a missing one, let's say there was no 49. There's a 49, I know, but let's say it didn't exist. Then what you would do is you would just leave this 4 blank, so you wouldn't not write a 4. You still write a 4, but you just leave a blank next to the 4 because you want to understand that there's a gap present at the 4 if there was no 4 there. Otherwise, you're squishing the 3 and the 5 together. You want to actually show the gap, okay? So if there was a gap, you want to show it. You don't want to just squish them together, okay? And now lastly, we want to look at our key over here. And it says the key represents what it stands for. So 4/9 represents 49. And specifically, it represents the female student who reported having 49 pairs of shoes. So it looks like the variable that they were measuring was the number of pairs of shoes per student. So that's why they put in the key number of pairs of shoes, all right? So just keep in mind, 4/9 could represent 49 like here, but 4/9 could represent 4.9 if we were doing decimals, or 4/9 could represent 4,900 if we were doing thousands, or 4.9 million. So it really depends on the context of the question, what you're letting to represent your stem and your leaf. Now, often what we'll see in the form of a multiple choice is something called a back-to-back stem plot. So a back-to-back stem plot is just like the stem plot we talked about, but it actually displays two different subcategories of that same quantitative variable. So in this case, we have males and females. So let's say we were talking about the number of pairs of shoes that the students have in the class. Instead of just doing it in one stem plot, we could break it down into the variable of gender, and we could show the males separately from the females, and then we can do comparison like we just did in the last one. So back-to-back stem plot uses the same stem, but the leaves go differently. So the males actually are very straightforward in this case because you're still reading it from left to right, but the females are actually backwards because you have to read it from inside to outside. So one set of data is backwards. I'm going to write down read it from inside to outside, aka from stem to leaf, either way, depending on if it's left to right or right to left, okay? So it says down below, note, be aware when comparing and describing two distributions as a back-to-back stem plot that the distribution on the left is actually the one that's backwards. So this is the one that's backwards, is what we were referring to. The one on the left is actually backwards compared to the one on the right. So if you think it looks skewed left, it's actually skewed right because the tail you think will be on the left will be on the right or vice versa, okay? So if I'm describing the shape of the males here on the right, this is going to be pretty straightforward. If you actually turn your head and you looked at the number line horizontally from 0 to 5, you would see that this looks like the tail is on the right, so this is skewed right for the males. Or we could actually say just skewed toward the higher numbers because these are the greater numbers, right? But now when you look at the females, I'll use a different color like yellow. It kind of looks more uniform, which means like all the bars are about the same. It might be slightly skewed. It looks like it's skewed right, but it might actually be slightly skewed left because you think it's skewed right, but it's skewed toward the higher numbers. Oh, it's skewed toward the higher numbers, so it's actually skewed right as well. This is slightly skewed right. So that's a little tricky. We'll have to do some examples in class. Slightly skewed to the higher numbers, which is skewed right. If you want, say skewed toward the higher numbers. Okay, turn to page 13. Now we go on to histograms. This is getting long, I'm sorry. This is page 13. Histogram. So a histogram, basically, it just kind of connects a stem plot into bars. I know that's kind of an informal way of saying it, but whatever. The bars touch. And specifically important is we have categories, or we have intervals, or we have classes on the x-axis, and we group observations into these intervals, and usually on the y-axis we put frequencies of how many observations fall into these. This is also for quantitative data, by the way. Okay, so it says choose equal interval width. So let's say we want to make intervals of size 5. We would have to do all of them size 5. So like 0 to 4, 4, 5 to 9 is actually 5 numbers. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, etc. You know, those are 5s. Make a table that shows the frequency. So first make a frequency table. Then you draw the horizontal and the vertical axes. You label them, scale them, and then you draw the bars and make sure that the bars touch. Okay? So let's see one below. You've seen a histogram before, like maybe in middle school or something. So here we have a frequency table. On the left, as you can see, the intervals are called classes. So let's just write interval also so you know that's another name for it. And notice the intervals here are 0 to less than 5, 5 to less than 9. So it looks like it's a width of about 5. It's probably a little less than 5. And then these counts, another name for count is the word frequencies. Okay, so there's 20 in the first group, 13 in the next group, and if you add these all up, the total in the sample was 50. So now here we have the histogram, and the histogram shows the bars touching, as you could see, and this on the y-axis is the frequencies. So basically they took this table and they made it into a histogram, and they drew all the bars going up to 20, 13, 9, 5, 2, and 1. Now, it's kind of easy to describe the shape because you could kind of just look at it and you could see the tail. So where's the tail? It's on the right. So if the tail is on the right, it is skewed to the right. Okay. Now, on the bottom, this is important with a histogram because this actually showed up on a multiple choice and it was kind of tricky. It says we can't see individual data points within the histogram. So keep in mind we don't actually know the value of each data point. This is so important because we don't know if the number in this bar is 25 or 26 or 27 or 28 or 29. We don't know. So we can't say that the exact range is from 30 to 0, 30 to 0. We can't say it's 30 because it could be this point in here could be 29 and this point could be 1. So this could be 29 minus 1. Or this could be 28 and this could be 2. Or this could be 4. We have no idea. So basically you know the ranges of the values, but you don't actually know the actual maximum, the actual minimum, the actual median at all. So this says, do we know the value of the actual maximum, median? No, we don't, not necessarily. We only know the range or the interval that they fall. Important. Okay, I'm going to start. All right, turn to page 14. This is getting long, so I should probably talk faster. So here we go. Now we're going to talk about measuring center. So you remember SOCCS, S-O-C-C-S. The C stands for center. We can measure the center with the mean or the median. So we're going to start with the mean. The mean is the average. And you guys know in the past you would add everything out, up and divide by the total. Another name for the mean, another symbol for the mean is X bar. This is the sample mean. And you saw this in algebra 2 and trig. Now, very important to note that the mean is not resistant to outliers. And we're going to talk about what that means in a second. So let's look down below. Here are the data of the number of goals scored. So this is the same data from before. And here again, this is the dot plot, okay? So they found the mean, and notice they found the mean to be x bar equals 3.15. So that's the mean, or the average. Now, what did we say about the shape of this dot plot? If you recall, we said the shape was what? Skewed. Specifically, it was skewed to the right because we said there were two outliers on the right. So what do you think happens to the mean when you factor those two outliers in to the mean? So remember, to get a mean, we would add everything up and then you divide by the total, right? So if you're going to add up 1 plus 2 plus 3 plus 4 plus 5 and find the average, how is that going to be different than if you add up 1 plus 2 plus 3 plus 5 and then 9 and 10? That 9 and 10, those outliers are going to pull the mean up. Pulls the mean up toward them, toward the tail. And the tail is on the right. So that's why we say it's skewed to the right, because it pulls the mean up to the right. So that's why we say the mean is not resistant to outliers, because the mean gets pulled up in the direction of the skew. So if it's skewed right, the mean gets pulled to the right. If it's skewed left, the mean gets pulled to the left. So notice here, it says, here is the mean number of goals scored by the 2016 U.S. women's team if we excluded the games that were possible outliers, the 9 and 10. So notice, look what happened to the mean. Now the new mean is 2.44. That's a lot lower than what it was before because the mean before was 3.15. So the mean definitely got increased before with the 9 and 10. And as soon as you remove those outliers, it got moved. So the mean is not resistant to outliers. A measure of center or any measure is considered resistant if it is not altered by outliers. What do I mean by that? If we remove potential outliers from the pack, like above, the 9 and the 10, and this value remains the same, it's called resistant. Okay? So the mean is not resistant because when we remove those 9 and 10, it got moved, it got changed, and it decreased to 2.44, not resistant. But you know what is resistant? The median. And the median is resistant because it's the middle number. And if it's in the middle, do you think it's going to be impacted by outliers on the ends? It's not. So the median is resistant to outliers. Why? Because it's in the middle. So it says which measure of center is resistant? The median is, because removing outliers on either end will not alter the placement of the median. Okay? Now, we said before the median is the middle number. Okay? There is a way of finding the median. There's a formula that we can do instead of crossing out 1, 1, 1, 1 like we did before and finding the one in the middle. The formula is take the sample size, which we'll call n, and do n plus 1 divided by 2, where n is the sample size. So let me show you what I mean by that, okay? Above, if you remember the soccer goals, there were 20 in the sample games. So I could do n plus 1 divided by 2 to get the location of the median. So 20 plus 1 divided by 2 is going to be 10.5. So the 10.5th observation is going to be the location of the median, which means it would be the average of the 10th and the 11th data point. So basically, if I counted 10 and 10, this is the sorted data up above here. 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is the 10th observation, and this is the 11th observation. The median would actually be the average of the 10th and the 11th observation, which is 2, because 2 plus 2 divided by 2 is 2. So the median would be 2 goals scored, which I think is what we said before. All right, people, we're almost done. We're on page 15, top of page 15. I know this is long, but it's going to be worth it, I promise. On top of page 15, we're doing comparing the mean and the median. So very important to note, if a distribution is skewed, the mean gets pulled in the direction of the skew. So I'm going to write that down. The mean gets pulled because it's not resistant in the direction of the skew. The mean gets pulled in the direction of the skew. Okay, so what do I mean by that? Well, if it's skewed left, as this first picture here on the left, the mean gets pulled down toward the outlier. So because the tail is on the left, the outliers maybe are on the left, the mean gets pulled to the left of the median. So the mean is less than the median. So when the mean is less than the median, it's skewed left. If it is skewed right, like this one in the middle, there are outliers on the right. The tail is on the right, so the mean gets pulled to the right. So the mean becomes greater than the median because the mean got pulled up. And then if something is approximately symmetric, like this last picture, the mean doesn't really get pulled at all. So the mean and the median are about the same, okay? So what you need to know is if you look at the location of the mean, that's going to tell you the direction of the skew. If the mean is on the right of the median, it's skewed right. If the mean is on the left of the median, it's skewed left. And if the mean equals the median, it's symmetric or approximately symmetric. So that's what we're going to fill in the blanks here. If the mean equals the median, like this case number 3 here, then it is symmetric or approximately symmetric, depending on if it's perfect or not. If the mean is greater than the median, this is a greater than sign. Remember, the greater than sign is pointing to the right-hand side of the number line, or you can make a G out of it for greater than. Then it is skewed right because the mean gets pulled to the right toward the higher numbers. And if it's a less than sign, the mean is less than the median, then the distribution is skewed left because the mean gets pulled down toward the negative numbers. So if we want to locate the mean, all we have to do is look at the direction of the tail or the skew, and then that's going to tell me where the mean is going to be pulled. All right, so now we have a question below. Look at the bottom of this page, example 7. How many likes on Instagram for the American Statistical Association? So they have 10 posts and they recorded the number of likes. So the first thing I want you to do is calculate the mean. So that's the average. So to find the mean, remember you're going to add them all up and divide by the total number, which there's 10 total in the sample. So that's n equals 10. So find the average. And then it says posts 15 and 16 are possible outliers. Calculate the mean with the other 8. What do you notice? So basically this is saying if you had removed the outliers and found the mean, the new mean, or the new average with those only those 8, what would the mean have been now? Then you're going to find the median, which is the middle number, first part C. When you do that, don't forget you have to list them in order from lowest to highest to find the median. And lastly, compare the mean and the median. So where is the mean with respect to the median? Because that's going to tell you the direction of the skew. So if the mean is greater than the median, it's skewed right. If the mean is less than the median, it's skewed left. And if the mean equals the median, it's approximately symmetric. Okay, so do this question now. Now we're going to go to the top of page 16. And page 16 is going to measure spread. Another word for spread is variation or variability. So that's a synonym. Remember when we're doing our SOCs, S-O-C-S, the last S stands for spread. So there's a few different ways that we can measure spread: the range, the standard deviation, and the IQR. So we're starting with range. The range is the one that you learned back in the day when you were younger. The range is just maximum minus minimum. Maximum value minus minimum value. That's the easiest thing to do to measure the spread. The problem is the range is not resistant to outliers. And the reason why it's not resistant to outliers is because if you're doing the maximum minus the minimum, if the maximum or the minimum are an outlier, then it will reflect that. So here is the data, the number of goals. Like we said before, we got to do maximum minus minimum. So the maximum value is 10, the minimum value is 1, 10 minus 1 is 9, so the range of goals was 9 goals. So that is a reflection of how spread out the data set is. Standard deviation. Standard deviation is something that you learn in Algebra 2 and Trig. Standard deviation can be measured with either population standard deviation or sample standard deviation. Over here they're using SX, which is the sample standard deviation. And basically, what does it measure? Okay, this is actually going to show up maybe in the form of a multiple choice where they ask you to interpret standard deviation in the context of the question. So standard deviation measures, on average, how much each value in the data set deviates from the mean. Okay, so we'll get a minute to write this down and then I'm going to explain. On average, so it's like the average of all the deviations from the mean. So how far is each value from the mean? So if a value is at the mean, then it has no deviation from the mean. So the deviation from the mean would be 0. If it's above the mean, the deviation would be positive. If it's below the mean, it would be negative. So basically, we have to first find the mean, which is not resistant, and then we have to figure out the deviation of every data point from the mean and find the average of all those deviations, basically. So it says Sx is always greater than or equal to 0 because it's always like a distance and it's always positive. So even if a data point is below the mean, we're going to find the distance from the mean. Larger values of standard deviation indicate greater variation. So the more you deviate, the more variable you are. So think about this. If you're a student who's very consistent, you get like 85 on every test, 85, 85, 85, 85. Everyone's getting an 85. Every test you get an 85. Then your standard deviation is low. It's like about 0 because you don't deviate at all from your mean. Your mean or your average is 85 and you're getting all 85s, then your standard deviation is 0. But let's say you're someone who's all over the place. You're very unpredictable. So you're getting like a 95, a 75, a 60, an 80. You're all over the place. Then let's say your average is an 80. Your deviation from your mean is going to be very high because you are very all over the place. You're very variable. So the higher the standard deviation, the greater the variation or the less consistency. Okay. So if you're very consistent, then your deviation is low. Standard deviation is not resistant because it uses the mean, so it's not resistant because the mean is not resistant, okay? The AP test has sometimes asked students to interpret the standard deviation in context. So here's an example. And I starred this because I have seen it in the form of a multiple choice and a free response. So it says, 11 high school students were asked how many close friends they have. Here are their responses: 1, 2, 3, 4, 6. So they did the standard deviation of these responses, and that's the sample standard deviation SX, and they got a standard deviation of 1.34 close friends. So if we wanted to interpret this in context, we say either a typical or an average. Another word for typical is average. The average deviation from the mean is 1.34. So a typical number of close friends that a high school student has deviates from the mean number of close friends by 1.34 close friends. So it's the deviation from your average, about plus or minus 1.34 close friends. All right, so that is the standard deviation sentence. And then another thing to note is if you see the word variance, the variance is just the standard deviation squared. So to get the variance, all you have to do, it's called VAR, variance, is you do standard deviation and then you square it and it becomes variance. All right. So there are two forms of spread that we talked about on this page, range and standard deviation. Now if you turn to page 17, we have one more important measure of spread, and that's called the IQR. The IQR is known as the interquartile range. And to get it, we're going to do Q3, which is the third quartile, minus Q1, which is the first quartile. So the quartiles are going to come from the 5-number summary, and they include the minimum value in your sample, Q1, which is the first quartile, the median, the third quartile is also known as the 75th percentile, and the maximum. So this can all be found using the calculator, by the way. So if we want to find the IQR, the interquartile range, we're going to do Q3 minus Q1. And that's going to give us the middle 50% of the data. That's this, the middle 50% of the data. And because we're using only the middle 50% of the data for the IQR, it is resistant to outliers because it's in the middle and the outliers are on the ends, so they don't influence it. All right, so we're going to be able to get the 5-number summary for a data set in our calculator. I'm just going to put a star here and I'm going to say calculator. Since we don't have our calculators in front of us, I'm not going to go over how to do that just now, but just know that when we get to class, we're going to be able to get our calculators. I'm going to show you how to put everything in the lists and to run the one var stat, which is one variable statistics on the list, L1. And we're going to be able to find the mean, the median, and the 5-number summary using that. Okay, so keep that in mind. And if you took Algebra 2 and Trig, you learned how to do that last year. You learned how to press stat edit, enter your values in the calculator, and then run the one var stat. Now, if there's any one thing that could be one of the most important things in this entire packet, I have finally come to it, and that is the outlier formula. So I'm going to put like a really big star around this, and I wrote, please memorize this. This formula is really important, and it does not show up on the AP reference table, so you do need to memorize this. And this is how to formally calculate outliers, so how to really calculate if outliers are officially outliers. So we may see some data points and think they're outliers just by looking at them because they look like they're visually separated from the data set, but that doesn't necessarily mean they're officially outliers unless they satisfy the following rule. So what you have to do is you have to first, I'm going to do the steps actually over here because I think this box is a little confusing. It says call an observation an outlier if it falls more than 1.5 times the IQR above the third quartile or below the first quartile. All right, so this kind of looks a little scary, so I'm going to write it out step by step here. Step 1, first you find the IQR, which is the interquartile range. To do that, as we said above, you do Q3 minus Q1. Okay, so first we do that. And then what we're going to do is we're going to multiply that by 1.5. So step 2, multiply 1.5 by the IQR. All right? And you're going to get a number. And then what you're going to do is you're going to add this number that you got to Q3 to get an upper boundary for your outliers, and you're going to subtract it from Q1, and you're going to get a lower boundary for your outliers. So you're going to do Q3 plus this number, 1.5 IQR, and you're going to get an upper boundary for outliers. And then you're going to do the same thing, but with Q1. You're going to do, I'll do it over here for Q1 minus this number, 1.5 IQR. And you're going to get a lower boundary for your outliers. Whatever is outside of these boundary values are considered outliers. So let's say my boundary values were like 7 and -2. If I have one outlier that's 10, 10 is greater than 7, so that's considered an outlier based on these cutoff points. Sometimes they call these cutoffs or fences. Another name for it is a fence. So instead of seeing the word boundary, you might see the word fence in here. Note, these numbers we calculate from the formula above serve as cutoff points for outliers. Any numbers above the upper cutoff or below the lower cutoff is considered an outlier. The cutoffs are just imaginary benchmarks we use to determine where the outliers lie. We don't actually graph these numbers when we make a box plot, but we just use them for our box plot to determine our outliers. Okay, so there's the formula. It is in the box, but I wrote it out on the side, nice and color coded for you. So these are the steps that you need to know. And it has shown up as a free response on the AP, but maybe not recently. All right, so now we're going to use this information for the outlier formula to make what we call a box plot. There are two types of box plots. There's a regular box plot and there's a modified box plot. We're going to talk about both of them here. So this one is talking about how to make a modified box plot. The modified box plot is the one that shows outliers. So it says, first, find the 5-number summary. Again, in the calculator, we could do that using 1var stat. Then find your outliers using your outlier formula. Then you're going to draw a horizontal axis, which is your x-axis. You're going to scale it out. Then you're going to create a box and whiskers. You're going to mark off your 5-number summary, which again is minimum, Q1, median, Q3, maximum. And then what you're going to do is you're going to determine if you have any outliers. You're going to make your box and your whiskers from there. Okay, so I'm going to show you what I mean by that. So let's say we have 2, 3, 4, 5, 6, 7, 8. Let's say my minimum was 2. I'm going to put a dot of 2. Let's say minimum was 2. Let's say Q3 was 3. So I'm going to put a dot at 3. Let's say the median was 5. That was Q1, sorry, Q1. Median was 5. So I'm going to put a dot at 5. Let's say the Q3 was 6, and let's say the maximum was 8. Okay. So once I have my 5 slashes, now you're going to draw your box and your whiskers. Start with your box, go to Q1, median, and Q3. I create a rectangle around those. So this is your Q1, median, and Q3. And then to draw your whiskers, you would go out like this and like this. This is your basic regular box plot. Now, let's say there was an outlier. Let's say I did my outlier formula and I got an upper cutoff for my outlier of 9. And let's say in my data set, I found out that the maximum was actually 10 and not 8. Then what I would do is I would go to 10 on my number line and I would draw a star. And that 10 would represent the outlier. And that one is not part of the whisker. And then I would go to my highest non-maximum, non-outlier maximum, and I would mark it with the upper part of the whisker. So basically then the outlier is separated from the whisker. Also note, box plots don't actually show individual values. They only show the 5-number summary. And this is important because we don't actually know how many points are in the data set by looking at a box plot. Whereas with a dot plot or a stem plot, we'll see every single observation in the data set. With a box plot, we're only going to see the 5-number summary and any outliers. We also don't see gaps or clusters at all or peaks. So we don't actually know if it were a histogram what it would look like. We just kind of know the 5-number summary. But it's kind of good. Now you can also determine if it's skewed or symmetric based on the box plot. So if you see that, let's say this whisker had gone over to 10, you would know that the whisker is longer on the right, and this would indicate that it is skewed right because the whisker would be longer on the right. If the whisker was longer on the left, it would be skewed left. And if the whiskers were totally symmetric, then it would be symmetric. Okay, turn to page 18. We're almost done. We're getting there. So now it says on the top of page 18, the modified box plot is the one that shows the outliers. I'm going to highlight this here. This is important. Shows the outliers separated from the whiskers and marked off with an asterisk or a point or a star or a plus sign or something. Basically, the whiskers are drawn to the largest maximum value that is not an outlier and the smallest minimum value that is not an outlier. Then the outliers are separated from the whiskers with the asterisk, okay? So here is an example below. Highway fuel economy ratings for 25 vehicles, okay? So the sample size here is 25. So as you can see, they wrote all the data out for us. And luckily, they have the Q1, Q3, and the IQR here. And actually down below, we have all the other information, so we don't have to put this in the calculator. Do you see that because this is sorted in order, we actually have the minimum and the maximum just in order. So the minimum is 21.5, and then the maximum is 23.5. So I'm going to add that in here. So when we do this, we're going to do minimum, Q1, median, Q3, maximum, okay? So the minimum I circled on the top is 21.5. The Q1 is here, 22.2. The median is here as well. No, it's not. Oh, but it is down below. Thank goodness, because I don't want to actually go find it right now. It says down below the median is 22.4. I could have found it by doing 20. Oh, let's actually do that. I know that you don't want to do it because you're totally over it, but I'm going to do it. The median is n plus 1 divided by 2. Okay, so if there's 20 total vehicles, is there 20 total vehicles? What did I say? 25, sorry, 25 total vehicles. So we're going to do 25 plus 1 divided by 2. So 26 divided by 2 is 13. So the 13th observation is going to be the median. The location of the median is going to be the 13th observation. So basically, because there's 25, which is an odd number, it's going to be like 12 and 12. And the one in the middle is going to be the 13th observation. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. This one, if you count the other way, going from the left. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 22.4. So there's your median, 22.4, which we said below. Q3, 22.6, and the maximum we said 23.3 up here, okay? All right, so now what are we going to do with this information? Well, we're going to do the outlier formula. So it says perform the outlier formula. So the outlier formula is step 1, find the IQR. So we're going to do Q3 minus Q1. So we're going to do 22.6 minus 22.2. Okay, so if you need a calculator, that's fine. Do 22.6 minus 22.2. We're going to get 0.4, and then we have to multiply it by 1.5. So I'm going to write that down as well. 0.4 and 0.6. So this is 0.4. Step 2, we're going to do 1.5 times the RQR. So I did 1.5 times 0.4. I got 0.6. And then step 3, this is the part where you have to do Q3 plus this number and Q1 minus this number. So Q3 plus 0.6 and Q1 minus 0.6. I know I'm running out of space here. So the Q3 was 22.6. So I'll do 22.6 plus 0.6. And the Q1 was 22.2. I'll do 22.2 minus 0.6. All right, so I'm going to get my upper cutoff and my lower cutoff. Okay, so I'm going to move up a little bit here. So we're going to do 22.6 plus 0.6 and 22.2 minus 0.6. So I got 21.6 for my lower cutoff and 23.2 for my upper cutoff. 21.6, 23.2. Okay, so as you can see on this picture above, they have the cutoffs labeled with like little dotted lines. They're imaginary lines. We don't actually really graph them, but they have 23.2, which is right here as the upper cutoff, and then they have 21.6 as the lower cutoff. And then what you can see is there are a few points that are below the minimum cutoff, the lower fence, and above the upper fence. Because if you look, even if you don't look at this dot plot, even if you look up here, you see there is one point, this one, the minimum, that's below 21.6. It's 21.5. So that's one outlier on the lower end, which is shown here. And also the maximum was 23.3. That's bigger than the upper cutoff of 23.2. So there are actually two outliers present, and they are the maximum and the minimum. Okay, so now it says draw the box and whiskers. So we extend to the last data value that is not an outlier. So we have not our minimum yet. We have, here's Q1, here's the median, here's Q3. So we have them up above 22.2 here. Median, we have 22.4, 22.6 for our Q3. And then the lowest number that was not an outlier was 21.9. And the highest number that was not an outlier was 22.9. So 21.9, 22.9. So as you can see here, they extended this whisker to 21.9, the lowest non-outlier minimum. And then they extended this outlier here to 22.9, the highest non-outlier maximum. And then the last step is we put our outliers in with a star. So where outliers are our maximum and our minimum, 21.5 and 23.3. So notice now they put them in on the bottom here. 21.5 is a little asterisk and 23.3. Okay, so I'm going to erase that for a second, but I just want you to note that these outliers are stars separated from the whiskers. So actually now we could see the 5-number summary plus the outliers. And if I had to describe the shape on this, I would say it's actually approximately symmetric, because it looks like on either end, the box is about symmetric, the whiskers are about symmetric, and the outliers kind of look about symmetric. And this squiggly equal sign, by the way, means approximately. Okay. So now I'm done talking, and now you're going to do your final question, which is on page 19. It's going to put together what we just went over. So page 19, example 8, you're going to do this one now, and it's going to ask you to find the 5-number summary. So if you have a calculator, it is helpful to do this if you have one at home. If you don't, what you're going to have to do is list these in order and then find the 5-number summary, which is again minimum Q1, median Q3, maximum. So keep in mind that there's 10 total posts, so 10 total in the sample. So list them in order from low to high, starting with 8 and going all the way to 38. And then I want you to find all this key information here. And then you're going to do the outlier formula, and you're going to do a modified box plot. All right. Okay. I hope this video was helpful. And I'm sorry that it was really long. but I hope that it was helpful, and hopefully now you have a good idea of what we're going to start with when we get to school. We're going to start practicing right away with some of these questions that involve the key facts that we did in this video, and then also we'll do our chapter 1 test about a week after. All right, thanks for listening. Bye, see you soon.